Hello, everybody. Welcome to the Vast Data Fireside Chat. Glad to see you. We already have a very full room of 66 people, and it's only 1 minute into the hour, so this bodes very well for a lively discussion. If you guys could just take a minute and say hi and chat, maybe tell us where you're from. I'm particularly interested in knowing if any of you are going to be in St. Louis next week. So let's get some anecdotal data on that. Who's going to SC? Okay, we've got Phoenix in the house. Come on, guys. There's 67 of you. We got to have more than one of you chiming in. Plano, Texas. Okay. Alex is going to miss SC this year. Hopefully next year. We've got Chicago and Fairfax. Cameron from Livermore will be in St. Louis. Okay, one for the other side. Let's see who else we got. Maryland, New Jersey.
Jersey.
Blair is taking a pass. Yeah, New Jersey gets to come too. Becky. Hi, Becky. I know Becky from Clemson. She's not going to be attending in person. That's a bummer. We've got Brea, California, Palo Alto. Horst is joining virtually. All right, Cambridge, Peoria, Illinois, Rhode Island won't be it. Japan, we've got Japan in the house. Welcome. Welcome. All right.
Can you join a Zoom call non-virtual?
Are the people who are not chiming in not going to SC? That's very interesting. Most people aren't saying one way or the other. All right. So I think maybe we can get started even a little early because we've got so many people here already. Well, okay, they're still trickling. I'll be totally, give it just another couple minutes. The one good thing about, there are more than one good thing, but one of the good things about having gone through the past 2 years is that everybody is super familiar with Zoom now. So we don't have to have all that fumbling that we used to have about like not being sure how to join the meeting. So it does give us a kind of a platform that connects us all better. All right, we've got Justin from Albuquerque not going to SC. We've got Eden, Utah. I love the distribution. Not going to SC. I love that we have someone from Japan. Let's see, what time is it in Japan at the moment? My little world clock. 8 a.m. Okay, that's not too bad. All right, I think it is time to get started. Our joining has trickled down a little bit. So without further ado, I am going to turn it over to our host, Tiffany Trader, who is the managing editor of HPCWire.
Thanks, Lara. Welcome, everyone, to our fireside chat with Vast co-founder Jeff Denworth and HPC legend Glenn Lockwood of NERSC. We're very happy to have you all with us and hope that the first 40 of you who registered early are enjoying your wine and chocolate. Today, as you know, we will be discussing the divergent architecture infrastructure required to service the needs of AI codes along with classic simulation codes. We're seeing more and more of that, certainly watching that closely and following that closely and writing about it here at HPCWire. So the conversation will explore why HPC centers are trying to become AI centers and whether the scale tools and software can all be the same or not. You all know firsthand the challenges and the opportunities here. You've heard the data points about the data explosion and with the digital sphere on track to hit something like 200 zettabytes by 2025. So just jumping in, to make sense of these trends in this time of change and to discuss where HPC and AI are intersecting with storage. We have two of the foremost storage experts here with us. Like I said, we have Vast co-founder Jeff Denworth and Glenn Lockwood of NERSC, home of one of the world's fastest supercomputers with Perlmutter there. So we're going to hear what they have to say, and we will be fielding questions along the way, given this is a sort of making this a fun chocolate and wine evening hours event. So you can drop those questions into the chat window, or you also have the opportunity to click on the raise hand button. And if you don't get your questions addressed right away, we'll have some additional time later for more Q&A. So from here, enjoy your wine, pretend you're at your favorite speakeasy. I can tell Glenn and Jeff are doing just that in your favorite city. And let's start. Let's start with Jeff. Could you tell us a little bit about who you are and what you do, and then we'll open it up to go over to Glenn, and then open it up to some discussion.
Surely. I'm Jeff. I'm head of marketing, head of products, co-founder of a storage company called Vast Data. I've been in the HPC industry for about 20 years. I actually started cutting my teeth at Livermore when I was working on some of the ASCII systems, selling some products for that, and then joined the Luster team and kind of have been in storage for HPC ever since. Went to DDN, and then left and kind of went to start Vast.
Great. I'm Glenn. How about you? A little bio from you.
Sure. My name is Glenn Lockwood. I'm a storage architect at the National Energy Research Scientific Computing Center, otherwise known as NERSC at Berkeley Lab. I've been in the HPC business far less than Jeff. I think I'm in approaching 10 years now, 5 of which have been doing storage. And what I do for my day job is help figure out where we need to go as a center and in terms of storage and IO and how we get there.
Great. So to set the stage for the discussion, let's look at why is AI a discussion within an HPC forum? Why are we talking so much about AI within HPC?
Well, I'm happy to start.
Sure.
In short, the answer is performance. And so just like traditional supercomputing has always been about how much you can get done with how big of a supercomputer you have, machine learning isn't anything new, but neural networks have been around for a long time, but only recently have they become really viable as machine learning tools using deep learning and related technologies, because we now have computers that are capable of actually training these complex neural networks efficiently. So they're both very much performance problems focused on how fast you can process data and to get scientific insight.
I think part of the situation is that the technologies are all highly overlapping as you look at how to build AI infrastructure versus how to build HPC infrastructure. And so, if you have a practice and an understanding of how to build at-scale equipment that can go really fast, to Glenn's point, well, you have NVIDIA and other companies like this advising that you go and deploy very high-speed networking, and the codes are parallelized, so you need to think about MPI and different things like this. And so the way I see it is because there's such overlap, it's so easy for a classic HPC center to adopt AI. Now, very often in the commercial space, we'll see AI projects where customers have no ability to spell HPC, which is interesting. So they're starting to hire from places like national labs. But on the flip side, every HPC center now, I think, is starting to kind of slightly rebrand itself as a HPC or an AI center. Some HPC centers are going whole hog on AI, and I think it's because the infrastructure competence is so highly correlated.
How do you look at that at NERSC, the AI center versus the HPC center?
Well, it's they're not in competition with each other by any means. What we're seeing is that AI is not really replacing traditional simulations or traditional meat and potatoes. It's appearing in places as a supplementary tool, and so it's not like our workload volume stays the same. It's that it's increasing because of AI. So whereas there used to be a human in the loop manually sifting through data or looking at complex visualizations to try to find some sort of insight, now instead of having a person do that, you can have the computer do it and make much better use of people time. And so it's increasing the scope of the relevance of our center because it is an important part of the workload, and it's like a force multiplier in many ways because it does what it used to take a person to do. But as a result, we're continually having to expand and provide more resources, both for our traditional simulation and modeling workloads, but now additional resources to help with this new AI workload.
And as far as trends go, how quickly moving of a trend is this HPC plus AI trend? Is it, and how quickly is AI coming into your average HPC center?
That's a difficult question to answer. In part because AI got its start at the laptop scale in many ways, and so that's the natural place for researchers to begin applying it. And it's only over time as their problems get bigger and their competency in using AI to supplement their existing workflows increases that those workloads start creeping onto the big systems that we deploy. And so it's hard to really tell. The trajectory is certainly up and to the right. There's no doubt about that. But it's hard to tell what the next big breakthrough or the new component of a workflow that used to be done by a person can suddenly be replaced by AI and suddenly have a huge new footprint of AI workload that appears in our system that just was never there the day before because the technique wasn't developed to apply it.
Mm-hmm. Yeah, you mentioned laptops. I mean, on the one hand, you're saying that they're not a competition and that there's a lot of natural similarities to them, but like a lot of the languages and tools might be separate. Do you see that moving together to make things easier for both communities?
I would say so. I mean, the lingua franca of AI is Python these days, and we're certainly seeing plenty of that on our supercomputers. But at the same time, Python is creeping into just general workflow orchestration or as a glue language around traditional C++ or Fortran-based simulation. And so in that sense, they're very complementary, and there is plenty of overlap in that, which makes it easier to integrate AI with simulation.
And let's look at moving from that to the workloads, the storage workloads. How do the workloads differ when dealing with the machine learning, deep learning side versus the more traditional simulation side? And you're nodding your head, so you can keep going, Glenn.
Yeah, it's like night and day. So the way I think about it is that if you look at traditional simulation, the point of that, the scientific objective of that, was all in the data that comes out of the simulation. That's the whole point of doing all this math, right? And so from an I/O perspective, all the money is in how fast you can get your results out of the compute nodes into a storage system, because that's where the value is. In the world of AI, that relationship is completely turned on its head. The real value is in the data that you use to train your models. And so instead of really wanting to write out data quickly, your scientific productivity is limited by how quickly you can take in data. And it's a very different world. It's a very read-intensive world, and it's one in which the nature of AI is such that you want to statistically sample data to do training. And so the I/O patterns are not whatever you want to make them. They do have an element of randomness dictated by the scientific or the mathematical approach itself. Whereas traditional simulation, you just write your data out as fast as you can, however you can, and you don't really care what that entails as long as it gets out onto your storage system as fast as possible.
I think size is also a consideration there, Glenn. If you think about your average, large scale simulation, it's going to pump out, maybe using something like MPI-IO, I don't know, a 10 terabyte file that gets laid down on the storage, and it's kind of nice big sequential blocks that you get to write there. Whereas if I'm doing like a TensorFlow job, I might be randomly reading through some sort of series of, let's say for computer vision, series of images at like 100 kilobyte intervals. So you get like 10 megabytes a second from a hard drive in that case, versus you can drive a hard drive at full tilt if you're just writing to it sequentially.
Right. And to further your point, it's not the case that AI data is independent from simulation data. So your simulation might generate those multi-terabyte files, and you might need to read them right back in along with some experimental data from, say, a telescope to do an AI-enabled workflow. And so like I said, it's not one or the other. They're complementary, and AI is happening at the same time in many cases.
I'm not sure about that laptop comment, though. If I think about how to train like a speech model or a computer vision model, the term deep learning originates from a discussion about the capacity of storage, right? And I barely have enough capacity on my laptop to hold my PowerPoints, much less, do a training run, even though the processor is actually pretty good for that type of stuff. And so, we read a report a couple of weeks ago from an investor called Art Capital, and they said that if today a state-of-the-art AI model takes about $1 million to train, and we see projects that are being earmarked for like $1 billion of annual spend, in the future, it'll cost $100 million to train that same type of state-of-the-art model. And it's a lot of gear that's required to get to that level of accuracy that everybody's aspiring to. A lot of laptops.
Ideally, if you can pump $100 million into a model, you can afford a little better than a laptop.
This is true. This is true. And if you figured out a model that costs you $100 million to make, you probably figured out how to make a lot of money off that model. Yeah. Okay.
We have a couple of important questions coming in from the chat. Do you use the same interior designers, and how do we get one of those jackets?
So the whole, Kirsten on our team, she said, well, let's do a fireside chat. And I thought, over Zoom, that's kind of a weird thing. So we just figured we'd play it up. And these are velour jackets.
They're polyester. Let's not overstate things. They are.
What's the difference between velour and polyester?
Maybe someone can tell me.
Yeah. So you guys were talking about the way that the workloads have to address the different needs potentially for modeling and deep learning, machine learning versus simulation. So what do you think are about some of the common mistakes that organizations make when tackling that?
So we see the world through a very storage lens, and I think I could probably speak for Glenn a little bit and say that he sees the world through a pretty storagey lens too.
It's my job.
I guess if everybody's talking or listening to us, then we can talk about storage. The number one kind of, I think, fallacy that the customers kind of they lull themselves into is that into believing is that a burst buffer is an appropriate method of accelerating an AI workload, right? It's actually, to Glenn's point earlier, these technologies are almost diametrically opposed. The burst buffer is intended to kind of act as a shock absorber for large writes that go into a file system versus AI that wants to kind of walk through all of your data to give a model the most observances so that it can be more and more accurate. And so people, Enling Go of HPE has this great slide where he shows, classic HPC is a little data in and a lot of data out, whereas AI is a lot of data in and a little data out. And so the thing that we believe is that data has to be on flash in order to keep GPUs efficient. And it's a very expensive proposition for most organizations, but when you don't pay that tax, you pay the tax of GPU efficiency or you limit the data science initiative or agenda, because now you're telling your researchers that they can only actually make good use of a certain fraction of their data that may, be fortunate enough to be on flash.
Yeah, there is certainly a lot of room to play, which is one of the forgiving things about AI versus HPC. So for example, a pretty common technique now is to rely on node local SSDs to accelerate your AI. So you can get around these problems of requiring a whole bunch of flash by sticking an SSD in every node. You statically partition your training data set, for example, at the beginning of training, and then you just take that penalty by running through a lot more epochs to finally get to convergence. But there is a trade-off there. You're cheaping out on storage and implementing something very simple, but every single time you want to train, you're getting less efficiency in doing so because you're only able to sample a statically partitioned part of your entire data set. And so I suspect that, as the field of AI matures and people don't want to settle for more epochs and burning more, watts in their GPUs, just so they don't have to deal with the storage implications of not doing node local, but doing some sort of centralized repository of data. There's a lot of room to play there, depending on your level of sophistication.
We've also seen, and I'd be interested in your thoughts on this, Glenn. We've seen customers run network storage much faster than node local storage.
Sure.
And so, NICs are cheap, SSDs are arguably more expensive. And it's a function of like, how much do you want to put on your researchers and your DevOps team to go and like manage a pipeline, or, you know, how much do you want to just spend for some fast NICs and some fast storage?
Right. I mean, that certainly is true. I mean, a single NIC will get you a lot more bandwidth than a single SSD, and that's a trivial thing to figure out. You know, in taking that approach, it's then tempting to say, well, I already know how to do network storage. I'm just going to slap down Lustre or BGFS or whatever else, and problem solved. And that's not true. You're just kind of passing the buck and hoping, you know, just because your NIC is fast, that your backend storage and the access to it from your training job, for example, will be commensurately fast. And that's not true. Not all file systems are built to do that. And so again, it's you know, you can do the simple thing up front and pay the price later on, or you can, you know, take a much more painstaking approach up front, architect a storage and IO subsystem that works well, endure the pain of that, take a little longer to deploy, but get better productivity later on.
I think that's a good segue for talking more about IOPS, Glenn. And I was intrigued by your recent blog post titled "IOPS Are Dumb," where you did get into talking about file systems a lot there too. So what's your perspective on that?
Yeah, that was yet another example of me shouting into the void. I didn't have an intended audience there, but really that was the culmination of plenty of meetings with storage vendors where as I said in the post, the first thing they ask when they walk in the room is, well, how many IOPS do you need? And to ask that question, or even how many gigabytes per second do you need, is just extremely reductive, because I can tell you an answer, but I guarantee it'll be wrong. And that comes from the old way of designing storage systems in HPC, where you run one big job and its job is to checkpoint really fast. And that's the only thing that matters. That's the only yardstick. And that's just not true in modern HPC. Jeff, I know, you mentioned that you didn't quite agree with me on that.
You know, storage salespeople, marketing people are exceptional people, I have to say. But working with customers is really tough. And so, you know, nobody's going to bring in a electron microscope and put it over top of your data center and derive what your workloads need to be. I mean, we need you as Mr. Customer to kind of tell us what you need to some extent, right? Now there's solutions marketing and stuff like that around very popular applications, but I don't know how many applications are running at NERSC, like on Perlmutter right now, probably a few hundred, I'm guessing.
Yeah.
Right. So how do you size for that, right? There's no like benchmark run that even matters.
Yes, no, I mean, that's the reality of it, right? None of this is easy. If it was, we wouldn't have jobs. You know, from our standpoint, we could release all that information, but the one thing that we consistently get indirect feedback from vendors on is that when we issue RFPs with detailed workload analysis, at some level, it becomes an intelligence test for the vendor. Like, how many PhDs do you need to throw at this report we put out to make sense of what the correct solution is? You know, if every vendor had to do that as the low bar for selling a product, then there would be no storage vendors, or it'd be crazy expensive to buy anything. So I don't know what the middle ground is, but you know, I figure by complaining about it loudly enough and having Jeff tell me that I'm wrong, we'll slowly get to a happy place in the middle.
Yeah, I really like the article. I have to say, we do see customers that do really high IOPS write workloads, but not in HPC. Yeah, I was curious what specific thing triggered you to go write that pretty blunt instrument of a blog post. It's just like, IOPS are dumb. You know, prove me wrong.
I got 50 of those in the back of my head. It's just a matter of having the time to write it out.
Okay. Yeah, it's not an easy thing to size for an HPC center classically. And then, you know, when you add the additional dimension of, okay, we're also, you know, we have this AI center of excellence. It's not running on different equipment. It's running on the same exact equipment that we've been running. It's just the workload turns everything completely on its head. And that's another variable that storage companies have fun dealing with.
We got a little comment here. We got a comment here from Kevin. If this is your institution, your last name, GEML. My first 2 petabyte data set cost 250 million in 1985. Wow, that was me. It was all in tape silos in 2 buildings.
Wow.
And yeah, wow.
Wait, somebody's got to inflation adjust $250 million in $85.
Yeah, yeah. And yeah, democratization of storage. Do you think and then we have a question from Becky, and this says, do you think the VAST system is appropriate for a scratch system for researchers who are doing AI on the cluster? See VAST in the question. Did you want to grab that first, Jeff, or are you, Glenn?
I think the question is fundamentally flawed.
Sorry, Becky.
Sorry, Becky. Love you. But you don't really have a scratch. I mean, you do have output files, of course, and you have a little bit of a scratch pad, but AI is not really a scratchy set of workloads, right? It's more aggregating an understanding of all the information that's possible to kind of deliver up to these neural networks. I don't know if you agree with that, Glenn. Sorry, Becky.
Well, I'm not sure how much I'm supposed to say here, since you did send me this nice bottle of wine. No, I mean, the reality is, in my opinion, and I'm speaking just for myself here, is that VAST is going to be more expensive than a pure capacity play parallel file system. And it's not going to be as fast as an all-flash NVMe Lustre file system, for example. But the benefit that it offers is you don't need to buy one of each in order to run your full workflow. You get somewhere better than the performance of all disk, and you get somewhere better than the capacity of all flash, done in a traditional way. And so that's where it fits. So is it good scratch? It's fine. Is it good capacity? It's fine. But it's one thing that solves 2 problems, which is better than fine. It's great.
Rebuttal, Jeff?
Well, hold on. I want to fight Glenn on a couple things. We keep distilling this conversation down to like how many gigabytes a second can you get from an SSD, but there are other variables that doth make a file system go fast, right? I don't know if Kirsten probably will tell me I can't talk much about this, but we have a customer that just did an AlphaFold run, which is Google's like protein folding codes on our system versus Lustre and GPFS. And the factor speed up was something in the order of 5 to 10x between the 2 platforms. And it was just one machine. So the question is, why is that? And the answer was our ability to support distributed mmap in ways that parallel file systems were never designed to do. And so there are other considerations here besides just cheap flash. I think file system architecture is something that, 5 years into it, I'm still wrapping my head around everything that VAST has made. But we find these interesting surprises from time to time.
All right. And then we did get a comment. I don't know if you sent an extra bottle of wine to Becky, but she says, I appreciated Glenn's article, even so true, even for assisted men of storage. I think where you were just going, Jeff, is a natural segue to ask, how should organizations think about benchmarking infrastructure in the future? You want to keep going with that idea?
Well, Glenn's the guy, so
all right,
you get to talk now.
Yeah, it's a tough one, because the more accurate you want to be, the more complicated it is, because the closer you're getting to real life, and real life is messy. It's real workloads are messy. So I think a good first step, and this is where I'm stumping, is we need to stop thinking about storage benchmarks as just what's the peak gigabytes per second and what's the peak IOPS you can get out of the whole system running a single massive job in the absence of any other contention, because no one on the planet runs a storage system that has that workload, as far as I know. There's always going to be someone on a login node doing something. There's always going to be stuff happening. And like Jeff said, if you're at NERSC, like I am, at any given time, we may have 100 or more different workloads running and all touching the same file system at the same time. And so as a reasonable first step towards benchmarking is just realize that that one hero number, much like HPL and top 500, it's a valuable metric, but it's not the only dimension of performance. You have to start looking at, for example, what happens when two workloads are running at the same time and trying to do the same thing? What's the performance like for each of those? How much do they step on each other? Or what happens to someone typing in LS if someone else is running a huge training job? Does the person doing the LS freeze up? Because arguably that's a far more damaging to user experience than the person who's probably logged out and having lunch while their training runs. Those sorts of considerations are all different aspects of performance that really affect user expectations and experiences that have historically never been benchmarked.
That's so funny that you said that. The number one thing that our customers ask us to optimize for is LS. And the reason for this is because our customers are storage admins, right? And storage admins, more than anything in the world, don't like hearing from users that say that the file system is slow.
Oh, it's the
now,
worst.
You may have a $500 million supercomputer that's killing that LS job by running some sort of Nobel Prize winning code, and you'll still try to go focus on fixing that LS application because you've got a user that is upset. And I think interactive IO, it does pollute a storage administrator's conception of where storage value is sometimes.
Well, the reality is for us, we get far more tickets complaining about slow IO, which often means my login is hanging. And that may not have correct weighting when looked at from a scientific perspective. But the fact is, every time a user sends us a ticket, one of our staff has to answer that ticket. And so if 50 users are complaining about slow LS, how many FTEs of our time is that wasting over the course of a year? That's real money. And so there is something to be said about a file system that is not generating user tickets, as trivial as the problem being reported may be.
We have a customer that went from one Lustre-based ticket a day to never having a trouble ticket come in again. And this came from this idea that you can segment our system into independent controllers. And because there's no east-west traffic across a cluster, then the concept, we call it pools. You can limit the interactive IO to certain nodes. You can limit the batch IO to other nodes, and it keeps church and state very isolated, even though everybody can access the same data.
All right. I see a few more folks have joined our Fireside chat. Welcome. Please feel free to leave questions if you have any questions, please feel free to pop that in the chat window. Or comments, or raise your hand. Click on that virtual hand button. A couple have come in. We got Cameron Haar says that Google says $250 million in 1985 is 637 million today. So thanks for answering that question. Becky says we allow our research to leave their data on the system for 4 months. And scanning through there. Here's another comment from Rebecca Arney, I think. Networks are key in the equation. Might be a question. Networks are key in the equation. What needs to happen in this real pain points, etc.? For example, congestion control, NVMe over Fabric realm.
I did a webinar with NVIDIA the other day, and they said, the conversation was kind of like, okay, so what do storage people think about? And network attached storage people only think about the network in terms of like what they need to worry about in order to make a computer go fast. And it's really hard because you have all these different diversities of different types of networks, and you have certain applications that are optimized for RDMA IO, certain applications that are optimized for TCP IO. Now, in file system speak, NVMe over Fabrics is not something that an application would actually consume. A host wouldn't mount an NVMe over Fabrics block device. You would want something that would virtualize that and abstract it away such that you just get mount points, or in the S3 context, you get buckets. And so we think a lot about flow control, congestion control, global pause, and we advise that all of our high-scale AI and HPC customers use congestion control on their networks, even just for things like NFS over RDMA or GPU direct storage access, just because not turning that on makes for some pretty bad days from a performance perspective.
Yeah, I think you've just addressed a couple questions that have come in from Shiva R and iPad. So if that didn't address your question, please feel free to follow up again in the chat. Glenn, did you have anything further to?
No, I think Jeff said it's a hard problem. Congestion control is certainly an area that provides great benefit. We're certainly seeing benefits with it at NERSC. We're using Slingshot on our compute, and we've got very well designed Ethernet networks within our data center. And doing the network right is difficult, but again, it pays off in the end.
So this one came in, and I wasn't sure if it was tongue in cheek or not, but it's been put in the chat twice now. So Kevin Harms, so who won, Ethernet or InfiniBands? Okay, shall we move on to burst buffers?
I want to know Jeff's answer to this.
Well, okay, 5 years ago, NVIDIA is an investor in VAST, so I'm going to say this as nice as I can. 5 years ago, I would have said Ethernet for sure, and NVIDIA has nice Ethernet products too. But I think AI has found such a kind of it's become the killer use case for very, very high throughput networking. And it's critical to avoid that problem that Glenn was talking about with respect to the limitations of direct attached infrastructure, having to partition either your data sets or your jobs in kind of really restrictive ways. And so, I would say that I don't see a clear winner in that debate now going forward. And every day our InfiniBand interest kind of gets greater and greater across our customer community. So InfiniBand's not going any place anytime soon. Now, CXL becomes interesting because then you can start to build big memory clusters out of this next generation network. And I think CXL over InfiniBand or let's say some RDMA infrastructure is going to even breathe further life into the IB community. I don't know if you've been studying CXL much, Glenn.
Well, I have. Doesn't go beyond a rack. And
Sure.
So you can buy less InfiniBand and more CXL, or more InfiniBand and less CXL.
It's a transport, though, more than it is a hardware definition, as I understand. And you don't think you'll have greater than rack scale CXL in the future?
Sure, but what purpose would that serve? I mean, we've gotten really good at scale out by necessity.
VAST has like 6 different ideas for distributed CXL.
I'd be very interested in hearing about those.
Yeah. Okay, we can talk about that offline.
All right. Let's see. Well, I mentioned burst buffers. Which a few years ago you could basically, we're all here with our wine and chocolate. A few years ago, you could basically play a drinking game with burst buffers on a storage presentation. Anytime somebody said burst buffers, you could take a drink. Isn't this a transitory? Is this a transitory technology to get us all to flash?
It's a bridge. It's a bridge. Storage tiering, burst buffers, all of this. Burst buffers were just because storage systems at the architectural level weren't designed for log structured, very high speed flash optimized IO. And then you kind of play it forward. It's like, okay, well, now there's a new bunch of file systems that are log structured, designed for really fast flash. And if you can make it cheap enough, then you don't need an independent system to kind of coalesce writes. You can just start to move beyond the topic of a burst buffer altogether.
Sure, but you kind of glossed over the most important point. If you can make it cheap enough, flash is still pretty darned expensive compared to disk. There's still a multiplicative factor difference there. So it's interesting that you don't hear much about burst buffers anymore. And that may just be because that marketing term has fallen flat, but they certainly still exist. So if you look at all of the new big supercomputers, they all are hybrid flash and disk, with exception of Perlmutter at NERSC, which we went the all flash route. But that's a matter of economics, and it's just not cost effective to buy all flash for every purpose right now. And so, I don't know
I
how
think
long
that's a
it will
function
be.
of value. We have
Certainly.
customers that are building exabyte scale all flash archives.
Exabyte scale or exabyte?
Exabyte all flash archives. And the value for them is in not having to worry about, actually that comes back to AI. These are AI training environments that cannot abide any IO down to hard drives. And so I'm not sure I agree with you. I think it's just a function of what is the mission of the organization and how are you trying to drive infrastructure? You're advising for burst buffers, but we're sitting here talking about AI training. And that's a very,
well, that's fair.
that turns the IO flows differently.
If your AI training puts ads in front of people, and you will be paid for putting those ads effectively in front of people, and you can turn that ad revenue back into buying all flash, great. Unfortunately, those of us who are on the public dole, entrusted with taxpayer dollars, it's, you can't solve all problems with flash right now economically, as much as I hate to say it. And so that's why you see all of these exascale systems, which, mind you, are funded almost exclusively with public dollars, why they're generally hybrid disk and flash. It's just the most cost-effective, the best value optimum for the mission of those systems.
I think there are narrower and broader definitions of burst buffer. Would you mind giving us your working definition of what a burst buffer is, Glenn?
Gosh, at this point, it's any storage system that incorporates both flash and disk and something that has a single name attributed to it. And so, for example, the Frontier system at Oak Ridge has a single Lustre namespace with a large flash component to it and then a large disk component to it. And Lustre provides the mechanisms with the help of a software that's laid out on top to migrate data between flash and disk without changing where that file appears to be in the namespace. And so I would consider that a burst buffer. It's not as exotic as the first generation of burst buffers, such as the one we deployed with our Cori system at NERSC, where users explicitly have to instantiate bits of flash and declare where they want their data to be on that flash and for how long and things like that. It's becoming a much more seamless process. But I would argue any time flash and disk are combined into a single parallel file system, there's a burst buffer in there somewhere.
Here's a good follow-up question coming in from Kevin Harms. Is node local the new burst buffer? I keep hearing AI likes node local storage, but seems harder to use related to data movement.
I have very strong opinions about this, but Jeff, I'd like to hear what you have to say first.
I think it's a function of data set size. And so it really comes down to what is the artificial intelligence workloads that you're trying to drive, right? An NLP model takes a few gigabytes of data. Send that to the computer. If you're building a self-driving car, then you have probably somewhere between 50 to 500 petabytes, and there's no way that you can instantiate a good node local strategy with that. I think the other challenge is there are technologies that will kind of aggregate all the drives that you have across nodes. And the problem then becomes predictability, because you have a series of interdependencies that you create through building such a system. And it injects a lot of jitter into your storage experience.
Yeah, I would argue that no one actually likes or wants or needs node local storage. And so it's true the AI community often asks me for SSDs in every compute node, but that is not what they want. What they want is a storage system that performs and behaves like a node local SSD does, which to say it does not behave like a global parallel file system where users all are stepping on each other behaves. And so if you can deliver a file system that has very good quality of service and can effectively partition users from each other so that they're not directly impacting each other, and like Jeff said, there's less jitter, there's less noise, No user wants a node local SSD. They just want the experience of that. And there are ways to do that. It's just often easier to just pop an SSD in every node and call it a day. But that is not. I would say that is not the future. That's a band-aid over the real problem.
Got another question on this from Cameron Har. Glenn, you correctly state the prevalence of hybrid disk solutions, but you're also partly famous for your 30 petabyte all flash file system. Were you able to find metrics to make that cost effective?
Yeah, I've written along with my colleagues several papers about that. In fact, that was a very measured risk that we took that involved a lot of workload analysis and figuring and economic projections of where flash prices would be, along with some innovation in contracts and the way we signed contracts and did pricing for flash speculatively with a few years outlook. But what it amounted to is that we knew how much data our users were putting on our scratch tiers. With our previous system, we knew how much more throughput our next system would have, and we could enforce a purge policy such that we knew what the capacity would be that would satisfy our user requirements for scratch. And with some pretty good modeling of forecasting of NAND prices, we were able to realize that with a pretty nominal investment, we could satisfy all the requirements of our users scratch tier in all flash and not have to incur the complexities of going hybrid disk and flash.
Okay, we've got another follow-up question coming in from something was touched on earlier from Becky, and Becky, I'm gonna ask you to unmute. I believe you also have a comment about burst buffers, and then you wanted to ask a follow-up question. You should be able to unmute yourself. There we go.
Hi, Jeff and Glenn. What I was wondering, could you repeat the suggestion that you had about congestion control within a cluster? Are you talking about TCP type congestion control algorithms? Can you explain that a little more?
Sure. So I'm assuming one of two things when we talk with customers about kind of deploying high-speed either HPC or AI file systems. Number one is that they have a high-speed network that's attaching storage into the cluster. And number two is that it's either Ethernet or InfiniBand, right? These are kind of very basic assumptions.
Correct.
And so the common mechanism that our customers most often use to feed IO into their infrastructure is using a derivative of NFS or an extension of NFS called NFS over RDMA, which is basically, same capabilities and characteristics that you'd find often in a parallel file system. And so in order to implement this appropriately, we always ask customers to have either an extremely well-built InfiniBand fabric where you kind of get flow control for free as part of being an InfiniBand customer, or implement things like ECN, explicit congestion notification on your Ethernet fabric. And we would run RDMA over converged Ethernet, which basically rides on top of UDP, as a way to kind of just drive IO into your nodes and out.
What if you have both situations? You have TCP as well as IB.
Well, now I think we're maybe talking a little bit more about VAST, so I'll just address that really quickly.
Yes, I am. Yes.
We have a distributed set of front-end nodes. Our customers call these C nodes. And these can have different modalities or different network personalities. And so without the need for network gateways or things like this, you can have some C nodes on your Ethernet network. They can still run RDMA over converged Ethernet. Other clients can mount over TCP. It's a simple mount option. And then you could have other C nodes that talk out InfiniBand. And they can all be kind of aggregating one global file system. And so it's basically just an issue of just deploying some servers that present to different networks.
Okay, but in that situation, then if you have TCP, you don't need to supply a specific congestion control algorithm?
No. TCP is lossy. It's you naturally will expect to get lower performance than if you went kind of full tilt on RDMA networks. But the nice thing about, in particular, NAS is that kind of the native network protocol for NAS is TCP, so there's no issues there.
Okay. All right. Well, thank you very much. I appreciate that.
Pleasure is mine.
Thanks, Becky. And Becky had also noted in the chat, we tried a burst buffer, but the research done at Clemson University didn't really need it. And then we have another question. Go. Yeah, please go ahead and follow up.
I was just gonna tell Glenn that I wanted to go with the burst buffer, and it was based on information I found at supercomputing a couple of years ago. I went to some of the things at supercomputing. Anyway, so we started with a burst buffer, but what we found with our particular users, now we're not near as big as what you are, so you got to understand that. So we have a lot of researchers who do single node kind of things or single core kind of things. And so what we found is our large BGF parallel information system worked really just as well as what we had for our burst buffer. But that was just our particular situation. And it has to do with what our particular researchers are doing. So, and of course, that's a much smaller scale than what they do at NERSC.
Sure.
Thanks for the comment, Becky. We have another question coming in, and it's one that I like. It's from Rebecca Arney. It's one that I often ask. How are the hyperscalers and their buying power influencing the solutions, architectures, et cetera, that will win adequate adoption, cost, ease of use, et cetera? Who's first?
Jeff, do you want to take that first, or shall I?
I'm actually now kind of half wondering who talks to them more, you or I, because you said you do talk to them. I see two things happening. One is those customers are driving up the global volumes for enterprise flash drives far beyond what kind of legacy enterprise customers are moving to flash with. And as a result, we all get the benefit, right? So we're currently under 10 cents a gigabyte for the QLC flash that we kind of specify for our customers in terms of the dollar per gigabyte before things like data reduction. And so I think you could attribute a lot of that just to the buying power and the flex that comes from companies like Amazon and Microsoft and Google. And we actually try to use the same drives that they do so we can, in essence, draft the activity that's happening there. But the other big thing that I think is very ill appreciated, particularly in the HPC space, is disaggregation. The conclusion that was made about 8 years ago by Facebook that drives soon will be much slower than networks. That is the opposite of the situation we were in 20 years ago. And so, whether it's CXL and you've got rack scale memory, or whether you have full photonics across a data center, which is where everybody wants to go to, this idea that you can completely compose your data center on the fly using APIs is such a powerful concept. And we've taken that and we've basically abandoned the idea that you need to partition scale out storage by building a next generation data structure that is available from 10,000 machines simultaneously, so you don't need to have a controller that explicitly owns any piece of data. The only way that's possible is because of this kind of compelling event that's being driven by the hyperscalers, where one, they're pushing the network vendors much harder than I think enterprise customers did. And two, they're showing the world that there's all new architectures that can be built as a result of this new network to storage paradigm shift.
Yeah, I agree. There's, I have to confess that HPC, at least at the extreme end, has not done as good a job as we should have learning from what the hyperscalers are doing, in particular in reconfigurability and highly dynamic data centers and data center scale programming and configuration and things like that. But to Jeff's point about the price, that's a double-edged sword. So we gain the benefits of reducing flash prices that are driven by the demand of the cloud service providers. But I referenced before that we did an economic analysis of flash pricing to figure out if we could afford all flash for our Perlmutter system. And what we found is that we had to time our flash contract purchasing time at a time when the hyperscalers were not restocking inventory, because if they're buying up a bunch of flash, prices go up and the prices we pay go up. And so we need to interleave our purchasing between when they're buying up versus when they're in these dormant states. And so net benefit in the sense that they drive prices down, but you don't want to be caught at a time when you're competing directly with them on a limited supply basis.
Well, I think right now everybody's competing with everybody.
Sure.
Yeah.
A comment from Becky. Our next cluster is looking at composable options. So here we are, 56 minutes in. Somebody's brought up composability. Not surprisingly. Any thoughts on where storage and HPC and AI intersect with this composable architecture we're seeing a lot of activity on?
Yeah, I would say composability at present and in the near future really makes the most sense in storage because like Jeff said, this is very network dependent. But if you look at the latencies of other things like memory accesses and things of that nature, the performance hit you take by going to a composable, say, GPU-based system is very high compared to the latency of accessing something over the wire. Whereas the latency of flash, as low as it may be, is still quite a bit higher than the latency of high-speed RDMA networks, for example. And so we're at this nice position now where there's a lot to be gained by doing composable storage, but we're not quite at the place where we have the networks and the latencies that would make composable memory, for example, super attractive on a performance basis.
Okay. Anything to follow up on that, Jeff?
I'm thinking about DPUs, but I'm not sure we have time to
crack
open that can.
Move on to it. We were talking about the old saying that let's see, hard drives are the new tape and flash is the new hard drive. Will archives be made of flash in the future, and if so, when might we see that?
Never, I think.
Good answer.
And there's one.
Oh, you agree? They agree.
I'm going to talk out of both sides of my mouth. Just give me 1 second. First of all, if you take a flash drive out of production for 6 months, it starts to lose bits, right? You have just kind of like electrons that start fading away. And so flash was not designed for offline storage, unlike tape, unlike genomic data storage and things like this. I'm trying to poke one of Glenn's buttons now. But everything else I think will be on flash. So if you need less than a minute of latency, that'll all be on flash in the future. It's a certainty.
Yeah, I generally agree. I think the world will ultimately settle on some combination of flash and tape. And tape is pretty messy to deal with. There's a high bar to buy into tape because you've got to deal with robotics and moving parts and libraries and things like that. And so if you're a startup that might run out of VC in a year or two, you probably don't want to blow a bunch of money on a tape library. You might as well just spend it all on flash. But if you're like us and you've got 45 years worth of scientific data, that stuff's better off on tape for the reasons that Jeff said. You really don't want to rely on data sitting on flash drives, especially if there's risk of them losing power, especially in short order, because, for example, QLC, my understanding is that it tends to lose bits a lot faster when not supplied with power than, say, TLC or SLC. And so the cheaper your SSD is in terms of dollars per bit, the faster it is at risk of losing data if you forget to power it on periodically, which is the opposite of what you want for an archival media.
The irony is that startup will go and start up on AWS instead, and they'll use Glacier as their storage target, and they're back to using tape already.
But they don't have to manage the realities of tape themselves.
Yeah.
Jeff, so you said that everything's going to be flash except the archive. So, but I'll ask the question anyway. What about hard drives in the data center? Is there life left there?
I think it's a matter of time. I have to say, we just received a 100 petabyte order 2 weeks ago from a customer that just said, we're done, right? So everybody has their own adoption curve that they want to travel down. VAST is trying very hard to pull in the inflection point in the industry so that customers can kind of like turn the page on the hard drive chapter. But yeah, if you look at any analyst prediction, they're basically calling like 2025, 2027 for the inflection to happen. Glenn's wincing.
Well, an inflection, sure, but hard drives will be around for a long time still. I think we both saw that kind of wacky plot where, sure, if you draw two lines going this way and you don't make any assumptions about things that will happen in 5 or 10 years, sure, they'll cross, and one of them will go into zero, and then it'll go into negative, and the other one will just keep skyrocketing. But hard drives are still pound for pound substantially cheaper. Well, not literally pound for pound, but dollars per bit wise, they're substantially cheaper than even QLC. And so I don't know, Jeff, the day that you can sell me flash at an equivalent price to what we're paying for disk, you'll have me convinced. But that day is quite a ways away.
Give me a little bit.
Well, we're here in this exascale era, nearly there on the computational side and there on the storage side. So what's the next big thing on the horizon for exascale IO? Jeff?
Glenn's the technologist. Let's let him take a crack first.
Yeah, there's a lot of threads going in different directions here. So if you look at the 3 US exascale systems and what's been announced, that's a pretty traditional giant disk and flash Lustre file system. You've got one that has some kind of interesting hybrid disk and flash with some amount of reconfigurability in it. And you have one that's a pretty wildly new all flash object key value store that relies on the unique properties of Optane or storage class memory as an essential component of it, much like VAST does. And so which one of those will win? I don't know, but I would say that our money is on parallel file systems as they are today are not the way of the future. And so we're looking heavily at object stores and key value stores for the most extreme performance demands. But at the same time, reconfigurability is going to be an essential part of it, because at the end of the day, we have almost 10,000 users at NERSC, and not all of them want to take the plunge into an object or key value store. A lot of them just want a plain old POSIX file system. And so being able to provide what the storage that users want for each individual user can either be done by buying every user their own file system, which is not economical, or providing a degree of reconfigurability and dynamicism. And that's a very promising direction that we think has a lot of a bright future ahead of it.
Okay, just a reminder that you can drop your questions in the chat. Hopefully they're addressing the challenges and questions that you have, but if there are any other ones that you want their insights on, definitely put in the chat, or I can take you off mute to ask over the call here. Let's venture out a bit here and talk about some of the more exotic, wild ideas coming around storage with things like quantum computing, DNA storage. We did a piece on our sister publication, Datanami did a piece on gold storage a couple weeks ago, NFTs, blockchain. We got all those things swirling around. So any thoughts on any of those topics? Jeff?
Yeah, well, we're kind of keen to see where quantum computing and storage intersects. So far, you can't keep data in a state in a quantum computer for more than like a few, I think it's like nanoseconds or something like that. So it's not really an IO machine, it's just a probability calculator. So I don't really see much there. Genomic storage, there's some venture going into that right now. There's a few companies that are trying a go at it. I think the latency is probably worse than tape right now, so the costs have to be much better than tape for, I think, someone to consider that. I don't know anything about gold storage. I'm just going to hard pass on that one. Blockchain is interesting. Actually, there's a bunch of new file systems that are being invented kind of on the blockchain, right? IPFS is an example of one of those. Do you know it, Glenn, the interplanetary file system?
Oh boy, that name says it all.
I think it came out of Berkeley. It's not so far from you. Yeah, so that's actually a pretty popular like Web3 concept that we see starting to take hold. But there's a lot of other kind of technologies that I think have yet to be kind of socialized really far. But we see an opportunity for a lot of infrastructure convergence going forward, and that's going to be where our focus is.
Yeah, I'm not sure that there's any really compelling breakthroughs in storage media on the horizon. Like Jeff said,
what about SSDs that you can compute in? It's like what the
I do.
smart SSDs.
It's unclear what you could do with those, right? And so the most, we live in the world of HPC. I live in the world of HPC, where everything is scale out. And so in storage, that means scaling out without compromising data reliability and resilience. And there's very little work out there that goes beyond a single computational SSD, as that I've seen. And so my question is, what happens if you want to compute on an SSD that stores only one block of an erasure coded stripe or a compressed component of a stripe? That's computational ability in that SSD is suddenly not very interesting, because you still need to talk to all the other SSDs to figure out how to decode the data that you've got, unless you store it in some representation that is locally decodable. As Jeff knows, such technologies exist, but they're not getting a whole bunch of traction out there. And so it's very much a science experiment at this point. I would love to be proven wrong that that computational storage doesn't have legs beyond the traditional encryption and compression, which is kind of the only compelling use case I've seen out in the wild. There's opportunities, but I feel like there's a lot of mathematics that has to be done before we can really see the use of scale out computational storage. I think the closest we'll get to that is frankly something like VAST, where you have a lot of CPU in the data path. And if you keep scaling that out, you can add more computational performance to in the middle of where the data is flowing, and perhaps do more data manipulation on data in transit. But that's a pretty complicated thing to do.
Yeah, we went the other path. We just said, let's not have CPUs talk to each other at all, and let's build a better data structure. Yeah, I don't know of any HPC center that has any computational storage deployed, but maybe there are. What else? Anything else that's kind of on the horizon, Glenn? You're a guy that keeps up with the stuff.
A couple of years ago, nanotubes were very promising as a completely breakthrough media.
Yeah.
But if you talk to the people in the know, I mean, the technology exists, much like Optane technology existed for years before it was productized. But it takes a large volume customer to make it worthwhile for a volume manufacturer to go out and build a fab that will fab this stuff and ship it. And so a lot of these really wacky storage technologies, proof of concepts in a laboratory are fine, and they show breakthrough performance or cost or bit density or something. But until someone can make money actually manufacturing and selling that stuff at volume, I don't know. I don't see a place for them in the near future.
I agree.
We had a question come in. It's actually following up on a point you made, Glenn, a few minutes ago. Is that DAOs, which would be, I think that's distributed asynchronous object storage. Do you know what it's referring to?
Yes, so that is the exascale object store to which I was referring.
Good follow-up. And then I think this is an important topic for just a little bit more discussion. Security. This was from Becky. What about I lost it, but it was what about security issues with PHI data? I think that's public. Is that public health data, PHI data? Yeah. What about security issues?
I think there you're going to see a renaissance, actually, and it's being driven out of the database community. The conversation is moving to a concept called attribute-based access control. And we're finding that customers want to really articulate the standards upon their data kind of in situ, in a way where you can basically build a data platform that is designed for both data isolation when you don't have access rights to a piece of data, but also self-service by kind of instrumenting the system such that if there are certain attributes of a piece of data, the storage knows how to lock it down. Otherwise, it knows how to present, and in certain cases, even like charge back for access, kind of in a general sense. And so, yeah, I think there's going to be a lot that happens with security over the next 2 to 3 years. It's going to get very interesting.
What's the security perspective at a lab, at a nurse, at a lab?
Well, so I can't speak for the other labs, and they certainly have much more strict security than we do. Berkeley Lab is completely open. We don't do anything classified, nothing like that. And so fortunately, we don't have to deal with a lot of the problems that other labs and other sites do with HIPAA data, for example, or FIPS compliance or things like that. So my understanding of this is pretty limited, but I often get the impression that the federal regulations that govern data access and separation and things like that haven't caught up to the technology yet. And so, you know, I often get the impression that we're forced, or labs that have security requirements are forced to do things in ways that, by the spirit of what they're trying to protect, don't require quite as heavy a hammer. But like I said, it's not my area of expertise.
Yeah.
It's got to be pretty tough. NASA is a customer of ours, and they're telling us that, you know, people are coming at them trying to hack them like a few 100,000 times a day.
They're coming at them for what?
Just hackers trying to penetrate the data center.
Oh yeah, unfortunately, anything with the .gov is a fun target for a lot of people.
Yeah.
Well, here's a follow up to oh, and this is great discussion. We're just going to go about another 5 minutes because we got another interesting question. May pop up potentially. We're talking about the different ideas around storage. So this is from Wright. What about phase change memory? Phase change memory was a being discussed a few years ago too, and recently as well. Will it break through phase change memory?
Jeff, what is the future of phase change memory?
Oh, I am very uncomfortable in this conversation.
Is Octane
okay.
phase change memory or not?
Well, okay, so that answer is almost certainly yes, although Intel nor Micron will actually answer that question directly, if I'm not mistaken. And so,
well, I can put my speculation hat on. And so I'm a former material scientist, and I believe I've seen things where people physically saw Optane in half, and it's a chalcogenide, which is the prototypical phase change memory media. So
okay.
If it's not phase change memory, it sure looks, smells, tastes, and touches like phase change.
Did you taste it?
No, I don't think you want to eat that stuff.
It's like eating glass.
So you know, we're like the Optane poster child in the market. We started with this idea that you could shape writes down into QLC in the way that the NAND structures are designed to be written to, using a very high endurance, very low latency, persistent media that you get with phase change memory in the form of Optane. So we're, I think, one of Intel's larger customers. They're a great partner of ours. But Micron is kind of out of the race, and so it's Intel's, I think, the only company that has a phase change product, although I think there is, Glenn, maybe a phase change memory company as well. If
there are a couple. There's Crossbar was one, but it was filamentary. Yep. I don't know if they're still around.
Yep, Crossbar was one. That was the ReRAM stuff, if I'm not mistaken.
Which is fundamentally phase change, yeah.
Right, and so the market is kind of at an intersection right now where people are trying to figure out what happens next. We've subsequently qualified a second supplier, not so much because we were worried about Intel, but because we're trying to diversify our supply chain. And it turns out that people can take a 3 or 4 layer flash cell, multi-layer, 3 or 4 bit flash cell. And if they just use one of those bits, they can build a device that's nearly as fast as a phase change device. So we also work with the company that was formerly known as Toshiba, it's Kioxia, on a type of fast flash that they make. It's basically the same for our customers.
Yeah, that's fascinating. Great. Well, I'm not seeing any more questions. We've covered a lot of ground here, a lot of great topics, from the practical to the exotic to the research side. So as we wind down, let's talk about SC21, since it is SC season and SC21 is next week. What can we expect to see this year? Are you going to be there in person, virtual? Any papers that you're presenting that you want to clue us into, plug?
Glenn's got the papers, so why don't you go first?
What's your paper, Glenn?
Sure. So I just wanted to
Go to the
present a
screen.
couple AI adjacent presentations that myself and many of my colleagues at NERSC and Berkeley Lab are presenting. And these are not super deep and difficult to understand papers, which is why I think they're worth putting in front of a crowd. So all of these happen to be at workshops on Monday, so not too far off into the future. The first of which is a paper that I and a few others at NERSC wrote along with the help of VAST, challenges in benchmarking all-flash storage for HPC. And so we did a pretty thorough examination of all the ways traditional benchmarking fails to properly characterize complicated storage systems based on all-flash. And in particular, we used VAST. But as we say in the paper, many of the principles that we discovered, or the quirks that we discovered, probably also apply to things like Deos. So that's on Monday morning. We didn't talk a whole lot about the gory details of deep learning workloads and the implications on storage, but the second paper by my colleague Khaled, also on Monday morning, is a really nice, thorough breakdown of the MLPerf HPC benchmarks, including the IO implications of these AI training workloads and what that means and the design considerations that fall out of that detailed analysis. And then finally, there's a paper on MLPerf HPC, which is part of the ML Commons benchmarking effort that's being presented again on Monday morning. And this one is interesting because this is a training benchmark, but it penalizes you if you have to stage data into local SSD, because that time is included in the full training workflow, which is what this benchmarks. And so it's just an interesting perspective on what really is involved in running training, specifically on scientific AI applications.
That's a really nice lineup. I encourage everyone to check that out. If you're going to be going to supercomputing, I'll be there. We have some folks from HPCWire there. Stop by VAST booth number 710 and check out these sessions that Glenn and his colleagues will be presenting on. And feel free to reach out to VAST Data, of course, and you can also find them on Twitter as well. So with that, we're going to wrap up. And thank you all for attending. I wish you all a good evening and a good weekend and a good SC.